Okay, so last time we talked about how to make single crystal silicon. So now we will look at how to dope the silicon. So the dopant can be added. So the dopant can be added into the melt to provide the doping. For example, if we add boron or if we add phosphorus in the melt, so this is the melt, then the boron and phosphorus they will come to the solid. So then the solid will also be doped with the p-type or n-type doping. So ideally, the dopant concentration in the liquid is the same as the dopant concentration in the solid. But in reality, they are not. This is not the case. So generally, the impurities, like the dopant impurities, they prefer to stay in the liquid. So as a result, the dopant concentration along the bowl will not be uniform. So this is described as the degree of the segregation, which is defined as the CS over Cl. That means the dopant concentration on the solid side divided by the dopant concentration on the liquid side. So this is the degree of the segregation. So ideally, always if this is equal to 1, this is the best case. In this case, the dopant concentration on this side is always the same. So along the entire silicon, the dopant, like a boron, the concentration will be the same from the bottom to the top. But in reality, as I said, this one is usually less than 1. Here is the segregation coefficient. So for example, the best material, this is the best, but this is very close to 1 is to 1. So this is the best. As a result, so the boron doped wafer is cheaper than other wafers, because if you make a big cylinder, the dopant along the top and the bottom is more uniform than other wafers. So phosphorus 0.35, antimony, this is 0.023. So arsenate 0.3. So now let's give an example to calculate how many dopant we need to put into the melt in order to have a given dopant concentration in the solid. So here, so we want to know, we want to find the concentration of the phosphorus in the melt to obtain silicon doped with the 10 to the power 16 atom per cubic centimeter. For the phosphorus, segregation coefficient is given by 0.35. So here is Kd, it should be K naught, 0.35. So this is defined as CS over Cl. So the dopant concentration on the liquid is given by, this one is given by, so CS, this value here, this is the CS divided by Kd, 0.35, is given by this number of atoms per cubic centimeter. So next, we want to know how many grams of the phosphorus should be added in the load. That is 5 kilograms in order to have this dopant concentration. So you see this one, we have how many atoms per volume. So we need to find out the volume of this 5 kilograms of silicon. So volume given by mass divided by the density is this one, so give you this number. So once we know the volume and we know the volume concentration, so we can find out what is the atomic number. So this volume concentration times the volume. So here we have the volume come from the silicon and the volume come from the phosphorus. So this one can be ignored because it's really small. So then we know the volume here, we know the volume and we know the volume concentration we need this number of the phosphorus atom in total. So you convert this one into the how many mole. So this number divided by this Na, divided by this number. This is the Avogadro number. Na give you how many mole. So once you know how many mole you have, you know for the case of the phosphorus, we have 31 gram per mole. For phosphorus, 31 gram per mole. So this number times 31 give you this number. In that, you get 3.16 milligram. So you can see this number is milligram, and this is the kilogram. It's much smaller than the silicon. So now we want to know the dopant concentration. We want to know Cs as a function of the how many fraction of the liquid got solidified. So we want to know the dopant concentration along the bowl, along the cylinder. So at the beginning, so we have the volume is V0, the total number, I0 is the total number of the impurity items. Total number, so C0 is the initial impurity concentration. So obviously, so C equal to I divided by volume, the number divided by volume. So when as the liquid becomes solidified, so we have the total number become I and the concentration become C. So I means liquid. So in the solid, we have the volume Vs, C is Cs. S means, so S means here is solid. So obviously, so Vs plus VL equal to V total volume. So Is equal to total. So obviously we have this kind of relationship. So in order to find out this formula, we do the differential equation. So during the growth, additional volume of dVs freezes. So the impurities incorporated into this volume is given by DIL. So how many impurities get in? How many impurity get into this solid is given by DIL. Minus, so we have minus because this one is lost. The IL becomes smaller and smaller, so we have minus. Now this one K naught CL, this is the CS. So CS times dVs. So CS times dVs, so we have the minus sign. So CS, we know that CS is given by K0Cl. So we have this formula here. So on the other hand, so Cl is given by I, the number, divided by the volume VL. So VL equal to Vs, V naught minus Vs. So we have this one. Then you bring this one to the left side. So you have the Di over I, then dV over this one. You put this one in the front. But this one is I naught to IL. This one is 0 to Vs. So this equation, So this equation can be, we do the integration. So in the end, we get this formula. So this is not hard. So we know that. So 1 over x dx. You know about this thing, equal to log, right? So we get this formula here. We get IL as a function of the volume ratio solidified. So C equals to I divided by the volume. So you put this one in, you get this number divided by the volume of the liquid. Then you define the F. F is the ratio of the solid silicon to the initial liquid volume. So then 1 minus F. So this one here is given by C naught. So you have this number here. So the CS, equal to CL. So you know the CL, and you can find out the CS by multiply by K naught. So you have here. So in the end, get this formula here. So now we look at the numbers. For F equal to 0, CS equals how much? Equal this one, right? So this makes sense. So CS equals to, for F equal to 0 at the beginning, the concentration in the solid is given by C naught, this number here, times K naught. How about F equal to 1? F equal to 1 equal to 0. So this one equal to infinity, because the value here is negative now, is less than 0. This K naught minus 1 is less than 0. So F equal to 1, CS equal to infinity. So how about if K naught equal to 1? If this equal to 1, then this term is 0. So the CS equal to constant. So obviously, K0 equal to 1 means there is no preferential segregation. So the volume, the dopant in the solid is the same as dopant in the liquid. Then along the volume, the CS is a constant, equal to C0, K0 is a constant. This one equal to 1. So CS equal to C0 throughout the cylinder. So this makes sense. So we can draw it. So we can draw this formula here, as you see here. This is F value. F is this value. F equal to 0. This one, the ratio is K0. So for the case of boron is 0.8, phosphorus 0.35, antimony, we know it is 0.023. So that means this number here is 0.8. So this number here is 0.35. This number here at this point is 0.023. So at the F equal to 0, the ratio is K0. F equal to 1, at this point, it is, as we see, it is infinity. It's infinity. Goes to infinite, right? And for the critical boron, the K0 equal to 0.8. It's close to 1, so it's flat. For the bigger other material that has bigger segregation coefficient is less uniform. That's why, as I said, the boron doped wafer is the cheapest because you have more uniform doping along the wafer. So here's the same drawing, but here we have the example of K higher than 1. But in reality, it's always like this. It's less than 1. It's less than 1. So now we look at flow zone growth. So what we talk about is called a CZ. This is called a CZ. This one called FZ, float zone. So Hershey is CZ, this is FZ. So why we need FZ growth? So we know that for the case of the CZ growth, so for the case of CZ growth, so we have oxygen and carbon. We have oxygen and carbon. So oxygen comes from this silicon oxide crucible container. Carbon comes from the heating element graphite. So this limit resistivity to about 20 ohm centimeter. But for the intrinsic silicon, the resistivity is more than 200 kilo ohm centimeter. So for the intrinsic silicon, so N equal to P equal to Ni equal to 1.45 times 10 to the power 10. So this is the intrinsic silicon. Resistivity given by 1 over Nie mu N plus Nie mu P. So mu N is the mobility. So Ni is this number, E is the charge of electron. Then you get a number close to this one. So this limit, so that means when we want higher resistivity, pure silicon, we need to go with the float zone growth. So these crystals, so this FZ crystal is more expensive and have very low oxygen and carbon. That is not suitable for the IC manufacturing. For the IC manufacturing, we need oxygen for the gathering. For the gathering process. So we will talk about gathering process in the next chapter. So for the FZ, for the float zone, we can get carrier concentration down to 10 to the power 11. So you see, this is the intrinsic 10 to the power 10. This 10 to the power 11 is very, very low. So it is not as common as the FZ grow silicon because it is more expensive. And the wafer size, it cannot grow 200 or 300 millimeter wafers. So FZ can grow up to 4 inch, which is about 100 milliliter. So the FZ is good for up to 100 millimeter of the wafers. It's good for the solar cells and power electronic devices that use the entire thickness of the wafer, not just the wafer surface. But still, I think for the solar cell, we use the CZ growth because this is cheaper. So this is how the float zone works. This is how the float zone works. So it's called float. It is called float because the melt is not held in a container. You can see the melt is floating. This part inside, so this is the melt, is floating. That's why it is called a float zone. So in the float zone growth, so the polycrystal silicon is converted into the single crystal silicon by the zone heating. So we heat it. We need to melt it in order to grow the single crystal. And we also need the seed. So this part is the C-mix crystalline. So we need the single crystal silicon. This one is the single crystal silicon. This is the seed for the growth. So we still need the seed for the growth. Then we move this coil. This RF coil. We move it up. But at the beginning we don't pass the current. So this part is not melted. Then we pass the current, so the silicon gets melted. Then we move this upward. Then we got single crystal of the silicon. So the thickness of the zone, the thickness is about 2 centimeters. So the height of the melting zone is about 2 centimeters. So we cannot make it the size here. It's up to, as we said, 4 inch or 100 millimeter, because this is floating. If it's too big, because the zone is only held by the surface tension. So only the surface tension held the liquid silicon. If it's very big, if it's bigger than 4 inch, then the melt zone will collapse. So we can use this one because for the float zone we want to purify. We want very, very, very pure silicon. That means this is also a purification process. So this is called zone refining. It's also called purification. So it is also called a zone refining. So this happened because the impurities they prefer to stay in the melt zone. As a result, if you do this several times. If we do this multiple times, we do the successful passing. We pass the melt zone one time, then we come back again, then we pass another time, we pass many times. Then the impurities will all be collected into this melt zone, into the liquid. As a result, in the end, this part here will be so very, very pure. Far away, this part here will be less pure. So this is called a zone refining. So how to do the doping? So usually when we do the float zone, when we do the FZ, we do not dope it. It is called intrinsic. Because for the float zone, we want high resistivity. So if you want doping, it is doable by gas doping. We can use the phosphine gas. So we can do this in the phosphine gas or diboron gas during the growth. Then those phosphine and the boron and phosphor will get into the silicon to become the dopant. Another way for the doping is called a pale doping. So we drill a small hole in the top of the EGS, electronic grade silicon rod. Then we insert the dopant. Then we use this. We do the zone refining process. We do the zone refining process. So because the dopant has a small segregation coefficient, so it is most of the dopant will be carried with the melt. So that means the dopant on the melt will be kind of constant. If the dopant in the melt is kind of constant, then the dopant in the solid will also be a constant. So we have a small non-uniformity. So this is good for the case of the small segregation coefficient, for example, gallium or indium. So now again, we want to calculate what is the dopant concentration along the bowl. What is the dopant concentration along the bowl? So we assume the zone length is L. That means the melting point, this part is L. The melt. So the melt is L. This is L. The rod has initial uniform impurity concentration with 0. So this one, before we do the zone refining, before we do the zone heating, we have the constant constant dopant concentration at C0. And also, to make it simple, we assume the cross-sectional area equal to 1. So the area here equal to 1 to make it simple. Then the volume equal to loss. If the area equal to 1, then the volume equal to the loss. So that makes sense. So now we assume that if the molten zone moves upward by dx, that means the molten zone moves to the right by the amount of the dx, Then we want to know the number of the impurities in the liquid, number of impurities in this liquid. What is the change of the I in the liquid? So we know that. So this part of the dopant will get into the liquid. So this is given by C0 dx. So this is how much get into. And this part, some of the dopant from the liquid, some part of the dopant from the liquid will get into the solid. This is the loss. This is the loss of the dopant from the liquid to the solid. So this is given by Cs dx. Cx, this set on the solid set dx. So Cs equal to K0 Cl dx. Then di equal to how many get in. So this is get in, and how many get out minus how many get out dx. So then we move the dx to the left, and we move this part to the left. So we have dx 0 to x equal to I0 to I, di divided by, we move this part to the left, C0 minus K0 over I over L. So this one can be solved. So in the end we get this formula here. So we know that for the Cs, it's given by K0 Cl, So this one, Cl, is given by I over L. So the area equal to 1, the L is the volume, right? So L is the same thing as the volume. So I divided by volume give you the C. So I0 equal to C0 times L. So this also makes sense. So I0 equal to C0 times L. This is what happened at the starting point. So at the starting point, we have this condition here. Then we bring this one to here. So we have here this term equal to C0L. So we have C0L. So we can take them out. The L is cancelled out with this L. C0 is taken out. So we have in the end we get this formula here. So here we can see that at x equal to 0, how much is Cs? X equal to 0. So this term is 1. This term is 1. So equal to C0 K0, right? So Cs equal to C0 K0 at the beginning. So this makes sense. Then x equal to infinity. Large number. So this term is equal so this term is very, very small. So we have the Cs equal to C0. That means it approach a certain value. So at the beginning, it is the Cs is reduced by this factor here. At the very end, it approaches. So something the curve will be something like this. So you can see it here. So at here the x over L, x equal to 0. So the ratio between the solid and the original doping is equal to K0, equal to K0. So this is 0.8, 0.1. So this one should be 0.05, not 0.5, 0.01. Then we have this one. So this is the x equal to small. When x equal to very, very big value, then it approach to 1. So the ratio, the Cs approach to C0 at large value, as you can see here. The Cs approach C0 at the large value. So this is the impurity. This is the dopant concentration as a function of different segregation coefficient. So if we do the multiple passes, with k not equal to 0.1, at the beginning, at the first pass, the 0 point become 0.1, so the ratio becomes 0.1. If we do the second pass, we have the square, so 0.01. Third pass, we have this one number cubic, so first pass, so something like this. So that means every pass multiple times, the impurity concentration become lower and lower. So this is the purified. It got purified. The silicon get purified at the lower X value. So this is called a zone refining, purification of zone refining. So now we look at the wafer fabrication. So roughly speaking, so we have the crystal growth with shaping, slicing, lapping, and grind, etching, polishing, cleaning, inspection, and packaging. So we don't need to know the details of each of the steps. So first is the grinding. If the diameter here is not 6 inch or 8 inch, so we need to grind it to have the right diameter, for example, 6 inch or 12 inch. Then we make the flat. So this flat tells you the crystal orientation. So otherwise, if you have a circular way, you don't know which direction is the 110 or 100 direction. So this flat tells you the orientation, direction of the crystal. So then we do the wafer slicing. Old times, so we use this kind of cutting. Nowadays, we use the wire saw. So wire saw cut the wafer cut the bowl into many wafers. So the saw blade is about 400 micrometer thick. So together with the loss and the seeds and the tail end of the crystal, so in the end, only 50% of the bowl ends up in the wafer form. So that's why, even for the solar cell, we know that the silicon is the main cost. So you may think, how about if we use 10 micrometer thick silicon for the solar cell, then we save the silicon cost. But actually this will not, because so even though the silicon wafer is only 10 micrometer thick, so in this cutting process, slicing process, lots of silicon is already lost. So in the end, we cannot save much silicon. So after the slicing, so we do a chemical etching process, This wet chemical etching is done using the nitric acid and hydrofluoric acid to form this etching product. Then we do the wafer polishing. So here, so we have the slurries. So we have something called a slurry. So the slurry contains two parts. One is the nanoparticles of the oxide or aluminum oxide. This is very hard. And we have the chemicals like sodium hydroxide. So during the polishing process, so we have the rotation and pressure. So they will generate heat. So this heat will drive the chemical reaction of the sodium hydroxide to oxidize the silicon. So the silicon will be oxidized with the heat by the sodium hydroxide. So this oxidized silicon can be removed by these nanoparticles. In the end, the polishing rate is much higher than pure chemical or pure mechanical polishing. So here is the common wafer surface orientation. So as we see here, so we have this flat. So this flat here tell you the wafer orientation. So this is the common way to tell the wafer orientation. For the P-type 100 wafer, we have big flat. This is the flat. We have big flat, and we have the minor small flat. For the N-type 100 wafer, we have the big flat and another minor flat here. For the P-type 111 wafer, one main flat. N-type 111, we have one flat here and another flat here. But this is not always the case. So I see that. So nowadays, even 100 wafer is often like this. It's only one flat. For the 100 wafer, because this is easier to make. You make only one flat. So when we break the wafer, we want to break the wafer. If we have the 100 type wafer, the flat here, the main flat is this is the 110. This side here. This side here is the 110 flat. 110 flat. So when we break the wafer, it easily break along this direction, easily break with the 110 plane. 110 plane. That means so we can break it along here, or maybe we can break it along here, perpendicular direction. It's difficult to break along this 100 direction. That means if you have the wafer here, you can break like this easily. You break like this. You break it into many pieces. So in the end, you get the rectangular shape. Each piece is rectangular shape for the case of the 100 wafer. So for the case of 111 wafer, so the breaking also along the 110 direction. So, but you break something, you will get something like this. It's parallelogram. So for the parallelogram, so one of the orientation may be this one may one. So this one is the 10 minus 1. So what's the angle here? What is this angle? So here you have 1 minus 1, 0, 1, 0, minus 1. So it break along this. It will break into not rectangular shape. It will be broken into. That means it will break. It will draw it here. It will be, I think, something like this. They will break. It will be broken into this parallelogram shape. So what's the angle here? So we assume that so we have A equal to 1, B. We have two vectors, 1, 0, 1. So the angle between this one and this one, this plane. So we talk about this kind of planes. So angle between this plane and this plane is the same as the angle between this direction and this vector and this vector. So we know that A dot B equal to how much? 1 times 1 equal to 1, 1 times 0, 0 times 1, so equal to 1. So this one equal to A times B times cosine theta. So A equal to square root. A equal to 1 square plus 1 square. So 1 square plus 1 square plus 0 square equal to square root 2. So this one equal to, so B is also square root 2, so cosine theta. So cosine theta equal to, this is 2, this is equal to 1, this is 1, and this is 2 equal to 1 over 2. So 6 equal to 60 degrees. And that means this every break, the 111 wafer is break like this, the angle here will be 60 degrees. So if you look at here, this triangular shape here, we know that, so this one here, so this line here, and this line, and this line. And those lines, this one is 1, 1, 0, this is 1 minus 1, 0, or this one maybe 1 minus. So those 1, 1, 0 lines, they have 60 degree. This is 60 degree. So I mean, buy the silicon wafers. So normally, a cheap place to buy silicon wafer is this place called University Wafers. For example, for the wafer, we care about first is the diameter. This is the 1 inch. So this is 50.8 millimeter. So this is 2 inch. So we also have 3 inch, 4 inch, 6 inch, 8 inch, 12 inch. Then is the type. So we have N-type, P-type, and undoped. So undoped, for the undoped, this one I see is the intrinsic float zone. So this is the float zone. So the other wafer is done by the CZ method, but this one is called FZ, float zone method. This is intrinsic, has very high resistivity. So this is orientation of the top surface. So normally we buy 100, but it's also possible to buy the 111 wafers. So this is resistivity, intrinsic higher resistivity. Wafer thickness, this is the polish. This is what called single side polish. So this might be called double side polish. That means both sides of the wafer is polished. So the grid attach the grid. Okay, thank you.